So I knew Todd at Duke, where he was a PhD student and I was a master's student. He would help me out with my math and tell me that an integral over a closed loop was not actually called an integral wearing a belt. And, you know, those kinds of things got me up to speed. I remember that. I remember that. We were staring at your whiteboard. But it's great. So it's good to come full circle and come back and have Tom Honey back here. And I want you to know my brother Ted, who's in the physics department here. And so it's a great honor to be here and to talk to you guys. So today, I want to talk to you guys about the work I do in the Arctic, trying to understand what's going on. Arctic's a really rapidly warming environment. There's a tremendous amount of stored carbon in the Arctic that's currently locked up in perennial frozen Earth called permafrost. And permafrost depths are increasing dramatically all across the Arctic. And soils containing a high amount of organic carbon, which have been frozen over the entire last ice age, are now becoming biologically reactive, starting to interact with the biosphere and with the atmosphere. And so that's the kind of work I'm doing. I want to tell you about that, and I also want to give a plug for this project, called the Polaris Project, where we take undergraduates from the US and undergraduates from Russia, and we go to a remote Siberian field station and work in the Siberian Arctic. And a lot of the work I'm going to talk today about relates from the Polaris Project. Now, I'd certainly love it if we had some students from the University of Richmond apply to go on this field excursion. We do it every July. I acknowledge my collaborators, Andy Lloyd, who's at Middlebury College, and Scott Getz, who's at the Woods Hole Research Center, and then I'm going to talk about some of my former grad student work, Logan Berner. Some of his thesis results are in this as well. So the Arctic is a really rapidly warming environment. These are data from where is it? From the NASA Goddard Super Space Studies that does temperature monitoring. And that figure on the left, you're looking down at the top of the planet, which is a view that I'm really used to, and maybe other people aren't. This is very hard to see. There you're looking at down at the top of the planet there. You have North America on the bottom, you have Asia on the top. And this is a temperature field looking at seasonal temperature anomalies from the last decade as compared to the 1950 to 1990 or 1980 climate normal, 30-year period of climate. And the Earth on average has warmed of about 1 degree over that time period. The Arctic, the northern high latitudes, has warmed about twice that rate. It's warmed about 2 degrees over that time period. And that's a basic prediction of anthropogenic greenhouse change, originally made by Arrhenius back in 1896. That as we put more heat-trapping gas in the atmosphere, the portions of the Earth that are dominated by high reflectivity and by long-wave radiation are the parts that are going to warm the fastest. And so the Arctic warming falls in line perfectly with how we understand the climate system to work, how we understand climate change. And there's a big role of things like sea ice having a role in that. So here's a paper, a snapshot of a paper, the role of between diminishing sea ice in the Arctic and the role of temperature amplification. So one of the basic feedbacks in the climate system is that you have about the brightest thing on the planet is sea ice that's been covered in snow. And so in the Arctic, during the winter months, and then over most of spring, over most of the fall, and over much of the summer, you have the brightest thing on the planet, which is sea ice covered in fresh snow. And that reflects most of the incoming solar radiation that's hitting that in the summer and reflects back out into space. As the climate warms, one of the sort of most basic feedbacks is that sea ice is going to diminish, it's going to shrink down, it's going to replace the brightest thing on the planet with about the darkest thing on the planet, which is ocean water. So as that sea ice retreats, you have started having dark ocean exposed, that's absorbing radiation from the sun, storing that energy, and amplifying the temperature impacts. And the sea ice gets a lot of press. And as well it should. Right now, this is data that I downloaded yesterday from a satellite that tracks sea ice. And it's really easy to measure sea ice extent. It's about the easiest thing to measure with a satellite, because you're looking at the brightest thing on the planet and comparing it to the darkest thing on the planet. So we have really good records of sea ice going back into the late 70s. And this year, our sea ice extent is right at the bottom here. We reached, oops, hey, it works now. This wasn't working before. We reached minimum sea ice in September, late September, and this is the 2011 data right here up to the day, the daily sea ice extent. This shows on the y-axis is the sea ice area in millions of square kilometers, and then there's a month on the bottom, and all the different color lines are different years. 2007 was the previous minimum sea ice extent record. And it looks like 2011 will almost certainly be the minimum sea ice extent record once the final data are in. And that's just the amount of sea ice covering in 2 dimensions. And we're definitely in the minimum sea ice volume. So if you look at sea ice in cubic kilometers, how much actual sea ice there is, both at its thickness. So we've lost a huge amount of sea ice area, and we've also lost a lot of sea ice volume. So what we've done is we've melted out most of the old perennial ice in the Arctic, and we're replacing with annual ice that forms every winter and then melts in the spring. And there's an excellent chance that during, within my lifetime, we will experience an Arctic that is ice-free during the summer. And that changes the radiation balance of the Arctic immeasurably. And so here's data showing sea ice volume from the Applied Physics group at the University of Washington, which models it. And you see that 2010, the triangles and blue line on the bottom are by far the lowest sea ice volume. We've decreased sea ice volume from this period from over 12 million cubic kilometers to under 5 million, about 5 million cubic kilometers. It's just a vast change in what's been going on in the Arctic. So there's big changes to sea ice. There's other changes, more charismatic things like polar bears floating on these chunks of ice that are left. Don't buy stock in polar bears, right? It's a bad time to be a polar bear. And it's almost certainly the warmest that we're seeing in the Arctic right now. This is paleoecological data from lake sediments and charcoal records showing what the temperatures look like over the last 1,000 years. This is a paper that was in Science, I think last year. This shows a temperature record with anomalies, how much the Arctic has changed. It's temperature on the y-axis and time on the x-axis, with the present being closer to me. Those are calendar years. If there are geologists in the crowd, geologists do it backwards. Geologists make time on that side, because I don't know why they're funny. But normal people put time going this way. And as you can see, the temperature record going up and up and up. And in fact, this long decline that was in Arctic temperature is sort of declining, going down. It's consistent with solar forcing of how we understand the planet system to work, and cooling from the late thermal maximum during the Holocene until the time we take the fossil fuel, we're taking carbon from the ground and up into the atmosphere. And Occam's razor sort of tells us when we take a heat-trapping gas and we put it in the atmosphere, we expect it to trap heat. And that's sort of what's going on here in the modern temperature record. The Arctic is probably about a degree, at least a degree, maybe 2 warmer than it has been over the last several thousand years. So it's an area with incredible change that's going on. The work I do has a lot to do, people talk a lot about sea ice and talk a lot about polar bears in the Arctic. The work I do has to do with what's going on with plants in the Arctic. And this was a paper that I suggested to Todd that he circulated among his students. Feel to read. This was an article by a guy named Matthew Stern, who's he studies the cryosphere, the world of snow and ice. And this is a neat article that came out last year in Scientific America, in the May issue last year, about what's going on the land surface as the Arctic warms up. It's an article called Arctic Plants Feel the Heat. And it helps illustrate sort of what's going on, what the relationships are between what's going on in the atmosphere, this surface warming, what's going on in the cryosphere as we're losing these huge amounts of sea ice, and then what the relationships are between what's going on between the sea ice, the atmosphere, and what's happening in the land surface, on the biosphere. And that's the work I do, has to do with the biosphere. This is a landscape that, one of the landscapes I work in. This is the Kolyma River in northeast Siberia. Vast, vast landscapes. If you've never been to the Arctic, you hardly appreciate just how big it is and how long it goes on, how far it is in between places. And there are no roads. You have to get to places on the waterways. And you can do that in the summer in boats or in the winter on snow machines or driving trucks on the rivers. But it's an absolutely vast ecosystem that is comprised of a very simple ecosystem. Structurally, it's very simple. It's only got a couple of tree species. It's mostly flat, and it's got perennially frozen ground underneath it. This is the Kolyma River in northeastern Siberia, which is where I work. Do a lot of my work. I work all across the Arctic. But this is focus a lot of my talk on what's going on the Kolyma River. So northeast Siberia, it's about where we work is about 69 degrees latitudes. It's above the Arctic Circle, 24 hours of daylight in summers. And it's an area that is changing very rapidly. When we talk about climate change impacts on a lot of the planet, they are abstractions. It's hard to actually picture what's going on. But in the Siberian Arctic, the changes are visceral. We see in the top right corner, there's forests that are, literally the trees are splitting in half as the permafrost underneath thaws and slumps into waterways, and as it slumps, the ground goes in half. So we see these trees that are split in half, and those are trees not long for the world. And as the permafrost thaws, you get actually these drunken forests, these forests that are leaning and falling over. And as they fall over and enter the waterways, you're taking all the soil carbon, you're putting it into the waterways, and it's starting to become reactive. It's being reacted. It's being respired as methane, it's being respired as carbon dioxide. You get lakes like this feature right here in the lower right. This is a feature called an alas, which is a drained lake basin. So that was a lake that the permafrost had thawed. The lake emptied out into that case the Coloma main stem, and you have this landscape feature that was aquatic and now is becoming terrestrial. And these are some of the features that we study up in there. The basics of what we try and do in the Siberian Arctic is we're working on trying to understand what's going on with the transport and transformation of carbon and other nutrients as they go with gravity from the terrestrial uplands, from the soils and from the forests, how that carbon is dissolved, moves into the wetlands, how that goes into the very small streams. What happens from the streams as it makes its way into lakes. From the lakes, it goes into the rivers, the Coloma main stem, and the other rivers that are up there. And then we also study the processes that are happening in the tundra, and ultimately all the way out into the estuary. And we do this with we have a good science station we work at in Russia. We study what's going on. We do primary work in the lab. We have a good wet lab. We have a gas chromatograph. We have a total sea analyzer. We have a lot of analytic techniques. We also have good biologists. We work with macroinvertebrates, and this is some of the work we do as part of this project called the Polaris Project, which I'll tell you a little bit more about. Why are we sort of all interested in this? I mean, the bottom line is that the Coloma River is a great model for understanding what's going on in the Arctic. It's the world's largest river that's underlain by continuous permafrost, so every square inch of that watershed is underlain by continuous frozen ground, right? Ground is perennially frozen. And that makes the watershed a really neat place to study as permafrost thaws. It makes it a very dynamic watershed because there's not a lot of room for water to say seep into the groundwater. Right? It's a very flashy place. You put snow, melts on it, runs out very quickly because there's very frozen ground. And its ecosystem is changing very rapidly as permafrost thaws. And the Coloma is this big waterway and this gigantic pipe that exports carbon out to the Arctic Ocean. The Coloma is exporting something like 3.3 billion kilograms of carbon per year out to the Arctic Ocean. And that's dissolved organic carbon. Carbon is dissolved in the waterways. It's particulate carbon. Okay, little molecule of carbon that are particulates. And inorganic carbon dissolved in particulate that's being transported out that way. A lot of that carbon is highly labile, and when the biogeochemistry of labile means it's really reactive. It's tasty for microbes. So microbes that are in the soils and in the waterways, they can get hold of that carbon easily and use it for energy. Okay, so bacteria respire carbon in the same way that you respire your breakfast cereal in the morning. Okay, you're doing the same thing. You're both heterotrophic organisms, you and the bacteria. You take cereal, you put it in your body, you exhale carbon dioxide. Bacteria get soil carbon, and they respire it, and they exhale either carbon dioxide or methane, depending on where they are, in the exact same way. It's the same exact process. The difference, as permafrost thaws, the difference is that the carbon that the bacteria are now able to access as permafrost thaws is just like your breakfast, but it's been in the freezer for the last 10, 20, or 30, or 40,000 years, and is now just becoming available. So we are really interested in how labile this carbon is. So as the land surface changes, how this carbon is going to be made available to the microbial community, and how it's going to make its way into the atmosphere through carbon dioxide or through methane. We're getting a pretty good handle after working in this area for a number of years on the processes that happen in the waterways. We're less sure of what's going on in the carbon in the forests, okay, so the terrestrial uplands, what's going on in the boreal forests, what's going on in the soils. I mean, we're working on now quantify our understanding of that carbon that's up there, and that's really what I'm going to focus on today, is the fate and transport of carbon in the soils and in the terrestrial uplands. Yeah, but a lot of it does make its way out through the waterways, through the estuary. So here's a quick bit of shameless recruiting. Part of something called the Polaris Project, which is an international effort to study the Arctic, and we do a field course in the Siberian Arctic every summer. We have the PolarisProject.org is our website, and we take undergraduates from different U.S. universities. We take about 20 undergraduates from both the U.S. and from Russia. We travel to the Siberian Arctic and do independent research projects and work with the faculty. It's been a fantastic project. We're going to year 5 of the project this year. And we do a lot of science communication. We have a lot of people, we blog what's going on live, and we try and communicate the science that's going on. We work with science photographers as well. One of the students that worked with us last year, her research project was just published in the journal Geophysical Research. It's a really great peer-reviewed journal. So that's the kind of work we're doing. It's very good science for undergraduates. I encourage anyone who's interested to come talk to me after. And I think applications are due in January this year. It might be December. It's one of those two. So I guess let's step back a little bit and say, why are we interested in the Arctic? And the bottom line is that there is a tremendous amount of carbon that's in the Arctic. And the climate change thing is really a story about carbon. And carbon's a neat element to study. If you are interested in carbon and it's in the atmosphere, you are an atmospheric chemist. If you're interested in carbon and it's in the water, you might be an oceanographer. If you're interested in carbon and it's in trees, you're a biologist. And if you're interested in, in permafrost, you might be a soil scientist. So carbon's this really neat thing. It cuts really across many different scientific disciplines. And it's just a fascinating thing to study. And so it's relevant to the climate change picture. It's also just a fascinating thing to study as part of Earth system science. And there is a lot of it in the Arctic. This is adapted from the Arctic Climate Impact Assessment, which is now getting kind of long in the tooth. But it's just estimates of different carbon pools in different places. So boreal lakes might have something like 120 petagrams of carbon. So that's 10 to the 15 grams of carbon. Which is 1,000,000 billion grams, which is like the number you make up when you want to say something's really big, right? And so there's something like 1,000,000 billion grams of carbon in the boreal lakes, and there's maybe 100 petagrams of carbon in standing biomass in forests, and maybe another 200 in boreal forest soils. And you add that up, and you start getting close to, you actually can exceed what's in the global atmospheric pool of carbon. How much carbon's in the atmosphere? There's probably something like, there's over 700 petagrams of carbon in the atmosphere right now. And there's this huge stock of carbon in tundra soils that are part of the active layer, maybe 100 petagrams of carbon. And then what's going on in the permafrost, you have something like in the upper part of the permafrost, continuous permafrost, maybe 10,000 petagrams of carbon that have been frozen and have not been part of the cycle of carbon from the atmosphere into the biosphere. Okay, it's been locked up. It's not part of the atmosphere-biosphere carbon cycle right now, but as permafrost thaws, it is becoming part of that cycle. Okay, and permafrost thaws is happening sort of ubiquitously across the Arctic, although it's patchy. And then there may be another 10,000 petagrams of carbon in marine permafrost, and you start looking at these gas hydrates, these carbon formations, which might be used in energy exploration. It's absolutely astounding how much carbon is up there. And it's very uncertain what's going on. It's very hard to work in the Arctic. It's logistically challenging. You can see that some of the errors on these, some of the estimates range quite a bit. And what I'm really interested in is trying to figure out how much carbon there is that could be part of the atmosphere-biosphere carbon pool, say, over the next century as permafrost thaw increases. And even if that permafrost becomes available, a little caveat here, it's not like it's all going to leap into the atmosphere and never come back. So you have plenty of, if you go out outside now and dig a hole, that ground is not frozen, and there's plenty of soil carbon in there, right? It just exchanges with the atmosphere. That's likely to start happening in the Arctic as permafrost thaws, and that's why some people, including we refer to this as the carbon bomb. Okay, this huge source of carbon that has been unavailable and is now becoming available to the atmosphere. And what do we know about the carbon bomb? How much carbon is there? How labile is it, which means how movable is it? What's likely to happen as permafrost thaws? Those are the main questions that drive the research that we're doing. So my focus is boreal forests. Boreal forests are the largest sort of intact forest ecosystem in the world. They ring the top of the planet, make up maybe 15% of the Earth's land surface, and range from sort of spruce and fir forests, spruce forests, in the Canadian Arctic to these vast, large forests that cover most of Siberia. And Siberia was not glaciated during the last ice age. It was ice-free all the way up to the Arctic Ocean. And the jet stream tracked up there, and there's a massive tundra ecosystem, a mammoth tundra steppe. And quite literally, you can trip over the bones of mammoths while you're up there walking around. I did that a few years ago. I fell on my face in the mud, and I turned around, and the students were wrestling up this gigantic thing, and they pulled out a mammoth femur and held it over their head while I was wiping mud off my face. And so there are quite literally mammoth bones literally in the ground up there. It's absolutely amazing. And as a result of this, the fact that this whole area was unglaciated during the last ice age means that the carbon that built up in that ecosystem built up very fast and has remained frozen. What happens up there is you get lots of transport of nutrients and lust materials up into the Siberian Arctic. This mammoth tundra grassland was preserved by mammoths eating the grass, trampling out down the vegetation, and depositing that carbon and excrement back onto the ground where it became frozen. It was still a cold polar desert, and that became preserved as part of that ecosystem. So this area accumulated vast amounts of carbon over during the last ice age. And that's why we're sort of most interested in this area of Siberia, where there's these very rich, carbon-rich permafrost complexes called Gedema. But the work I do is actually more boring than that. I work mostly in the boreal forest, which is, frankly, kind of a boring place. It's one species of tree. There's a Hawaiian larch up here. There really is only one species of tree. There are not two. Right? And if you were to go out onto the University of Richmond campus, out in the great forest around here, and look around, you could come up with 100 tree species out here right now. You go out and look around. Okay, the diversity for this biological desert up there. And these trees up here, this ecosystem that rings 50% of the Earth's land surface, is essentially an invasive species. Okay, this area is supposed to be mammoth tundra ecosystem, but it's not. Right? There's this brief interglacial period where this forest has grown up, but this is really a mammoth tundra ecosystem that has this invasive species. It's like kudzu in the Arctic. Okay, but there's a lot of carbon stored in this stuff. Okay, a lot in the standing biomass, a lot in the leaves, a lot in the roots, and a lot in the lichens that make up a lot of the overstory. So in this talk, what I want to do is talk a little bit about what's going on with land surface change up there, how that land surface is changing, how we've observed it change over the last few decades, how it's likely to change in the future. Talk a little bit about what's going on in the trends in tree growth up there, and what that means for the carbon cycle. As a result, we'll talk about this satellite index called NDVI, which I'll explain. But basically, when I say NDVI, you can just think of how green something is. Okay, it's basically a greenness index, and greenness is related to photosynthesis. And then I'll talk about some work we do with tree rings. Okay, so we'll talk about the relationship between climate and tree rings and the satellite index. And then we'll say sort of what's going to happen, where the research is going, and what's going to happen as the climate continues to warm. And maybe talk a little bit about what's going on with carbon. So the tree line across the Arctic, the land surface is changing really rapidly. This is a shot from Alaska, which shows how latitudinal tree line is moving northward, and these areas that have not had trees previously are now being invaded by trees. And tree line expansion is sort of ubiquitous across the Arctic, but it's idiosyncratic. Where trees advance depends on whether or not there's good drainage, whether or not there's permafrost northward of the tree line, and it's slow. And what happens when you have tree line advance, you take tundra, which is really bright and reflective. It takes a lot of radiation that comes in from the sun and sends it back out into space. When you replace that with forest, you make the land surface a lot darker. You make the land surface darker, you start absorbing a lot more radiation, and causing that to be then re-radiated out as long-wave radiation, causing atmospheric heating. So as the tree line moves north, they're actually darkening the landscape and making it, changing the Earth's radiation budget as a result. There's a lot more evidence, or a lot faster evidence of shrub expansion, which has been called the shrubification of the Arctic. The Arctic is, shrubs are moving forward into the tundra very rapidly across, all across the Arctic. And what that means is that woody plants, areas that traditionally tundra plants don't have, they're not woody, they're perennial plants, they're annual plants with perennial plants, so they don't form woody biomass, they don't grow upright. Shrubs are advancing out into the areas of tundra. As that happens, you get this like really cool feedback where as the shrubs move forward and they establish, they trap snow in the winter. When they trap snow in the winter, they actually help to keep the ground below them relatively warm. Because in the tundra, when there's no snow covering it, when the snow blows away, the ground is very, very, very cold. Okay, it can be temperatures are common in the -40s and -50s up there. When you have snow covering it up, it basically keeps it very close to freezing, right around 0 C. When you have something around 0 C, you have microbial activity. Okay, so you have nitrogen-fixing bacteria, say, in the ground. You have that happen, you're fertilizing the area around the shrub. And so the shrubs hold on to the snow. They have water during the season as that snow melts. They have enriched nutrients as the soil becomes richer around it. And they're excluding the lower plants from being able to come up. So there's this really cool system of propagation, this feedback involving snow and albedo and microbial activity. And it helps to thaw the permafrost as the roots go down, and that helps because it helps to transfer energy down into the soil, and that then paves the way for tree line expansion. So the changes in the near future in the Arctic from the land surface vegetation are really shrub related, but long term we're going to see lots of changes to the tree line as it moves forward north. And this has been this whole area, this whole idea about what the feedbacks are between the land surface has been this area of really sort of active thought experiments and field experiments, all this work trying to figure out what's going on there. One of the sort of really visionary thinkers and workers in this field is a guy named Terry Chapin, who's an ecosystem ecologist. And he published this neat conceptual model of what's going on there. The high latitudes warm, and you have changed circulation patterns, you have increased latitudinal transport of moisture transport up to the north, changing the radiation budget as the land surface darkens. But in terms of the terrestrial environment, he wrote this, that pronounced terrestrial warming in Arctic Alaska correlates with the lengthening of the snow-free season, which has increased atmospheric heating by about 3 watts per meter squared per decade, which is a tremendous amount. And this current continuation of current trends of shrub and tree expansion could further amplify atmospheric heating by 2 to 7 times. So we have this feedback we already documented between sea ice and atmospheric warming. That's caused the Arctic to heat about twice as fast as the mid-latitudes. And this work on the land surface suggests that as this amplification continues, the land surface can now start to kick in a feedback of darkening, absorbing of radiation, lengthening the snow-free season, which could increase warming another 2 to 7 times. So these massive feedbacks that are exacerbating warming that's already taking place. So the Arctic is running away in terms of its climate response as it warms. And we have identified all these positive feedbacks between what's going on with warming and the physical environment and the biotic environment. So sea ice, land surface, etc. One potential negative feedback, this is how I got into this game, was trying to figure out what was going on with the greening of what's been called greening of the boreal forest. So, you know, a really simple cartoon idea for how the ecosystem should respond is that, look, you got the boreal forest that covers 15% of the Earth's land surface. It's a cold limited ecosystem. You can only photosynthesize for maybe 12 weeks a year. So as the land surface heats up, those forests should be able to grow better, right? They should be able to grow earlier in the spring, better during the summer, and later into the fall. Maybe that's a negative feedback. Maybe that can actually, maybe they'll start stocking away carbon into the boreal forest. Maybe that'll be a negative feedback of climate change. And indeed, early studies using satellites looking down, we've had good satellites measuring vegetation from 1981 onward. We've had a satellite that gives us good records of how green vegetation is, using this thing called NDVI, which I'll explain. Has suggested that the Arctic was greening. Okay? The photosynthesis every year was increasing, okay? Which implies maybe a change in the carbon balance of the forests. So I'll use this term, this thing NDVI to talk about this. NDVI is this index that you can get from satellites. The satellites we use for this were not designed for measuring vegetation. They were designed for meteorological forecasting, and were used a lot for agricultural forecasting. But NDVI takes advantage of the difference in the spectral response, the kinds of wavelengths that are reflected off of dry vegetation or green vegetation or soil. And so these are different curves that show wavelength here on the x-axis and how reflected that surface is on the y-axis. And so the land surface of leaf structures and waters, it really reflects very strongly, sort of here in this wavelength, but there's a lot of absorption in this wavelength. And so you have chlorophyll, here you can basically exploit the difference between how much radiation is absorbed in the near-infrared part of the spectrum versus how much is absorbed in the red part of the spectrum. And by creating an index of that, you can very closely approximate how much chlorophyll there is. So this is an index that was developed for measuring agricultural productivity. It also applies to what's going on in the canopy of forests. So when I say MDVI, it's a measure of how green something is. How green something is relates very strongly to how much chlorophyll there is. How much chlorophyll relates directly to what we refer to as the gross primary productivity. Okay, how much biological activity is taking place, how much carbon is being taken from the atmosphere and stored in the plant as sugars through photosynthesis. So higher values of MDVI mean higher greenness, lower values mean lower greenness. Okay? So let's talk a little bit what the evidence is for what's going on the land surface and what now these trends are in the greening and the browning of the Arctic. When I started looking into this work in the about 2004, 2005, the suggestion was that the satellites showed that this long-term greening of the Arctic from about 1982 up to about 1991. But after that, the signal sort of changed. And we weren't sure if it came from volcanoes or Mount Pinatubo erupted in 1991. It might have changed that. But when I started coming along and reanalyzed this satellite record, the work we started doing at the Woodville Research Center and other places showed that, in fact, the boreal forest was not continuing to green. It was not, photosynthesis wasn't increasing, not everywhere. In fact, large portions of it were starting to decline in greenness. So this is, again, another picture looking down at the top of the planet. Here's North America. Here's Asia over here. These trends here, the green trends show places where photosynthesis is increasing, statistically significantly increasing. And to do this right, you have to take into account the autocorrelation, how related the growth is from one year to another. Areas in brown show areas where the forest was browning, okay, where photosynthesis was declining. Okay, so we're declining gross primary productivity in the forest, or at least as seen by the satellites. And we found a much less rosy picture. We did not, in fact, find that the dense forests, where there's already quite a bit of carbon, where forests could maybe perhaps take carbon out of the atmosphere, those areas are not continuing to grow. In fact, those areas are declining in growth over the majority of the of this belt over here in subarctic Canada. Big chunks of the interior. I think which is easier to see. Big chunks of the interior of Asia. And then there are these areas that are showing greening, okay, showing increased trends in photosynthesis. And we noticed when we did this work in North America, it was the non-treed areas that were showing increases in greening. And we found that in Russia, the places that were showing increases in photosynthesis were these very sparse forests where the trees didn't have a closed canopy. And what we suspect was happening is that the increase in greenness up there was not in fact trees, but was the surrounding vegetation, the tundra vegetation. And we found that on the most part, there was no trend. Okay, most of all, in terms of NDVI, in contrast to the cartoon model, the forests were not increasing their productivity. We found that in most cases there was no change in what was going on in the forest. But what we did find is that what was happening is that the that didn't change for you, huh? Just for me. There we go. The needle-leaved evergreen forests, okay, places that have spruce, have these trees that hold on to their needles for multiple years. Those places were showing 6% of those were declining in growth, only 4% were increasing. Larch showed more increasing trends in growth, okay, but that was turned out to be the very, very sparse larch forest, and it didn't translate into what was happening with the trees. So overall, we saw this trend of increasing greenness in areas that didn't have a lot of tree biomass, in declining areas of greenness in areas that had a lot of forest biomass. So clearly, the cartoon idea of what was going on in the Arctic didn't really pan out. Okay, our simple ideas about what was happening to the carbon cycle were not coming to fruition. This Scientific American article that talked about changes in the Earth's land surface as a result summed this up. It says that the satellite record revealed an even more startling result in the vast boreal forests south of and ring in tundra. Although studies confirmed that the tree line was continuing to move northward into higher elevations, in many places the satellites indicated that behind this advancing front line, or front, the forests were losing biomass and becoming less productive. The forests were browning, drying, and dying. while the tundra was green, a fact that seems to contradict the conventional wisdom concerning forest response to climate warming. Okay, this is this article by Matthew Stern summarizing the work that we had done with satellite indices. Which is right, it was really surprising to us. It didn't match the cartoon idea of what should happen to a cold, limited ecosystem when the temperature goes up. And you know, one of the coolest things that happens to you in science is, right, when you get into results you don't understand. And in this case, what was cool for me as a young scientist was that it wasn't just that the magnitude of our expectation was wrong, the sign was wrong. Right? We didn't even have the sign of the relationship, right? We thought that these things should be increasing productivity, and it turns out they were either not increasing productivity or declining productivity overall. And so that means you're kind of in for some cool science, right, when you have the sign wrong. What we want to do then is figure out what's going on. Well, how does this NDVI relationship to this greenness index relate to climate? And that turned out to be a fairly easy question to answer. It turns out you're able to model this gross primary productivity really easily with satellites. So the satellite records between NDVI, which is the black line on there, it turns out we can model that really carefully when we model what's going on average temperature, which is in the red, and then precipitation, which is in the blue, and we're able to create these statistical models that can predict how green something is based on the climate that's around it, which is cool. That shows us that the change in summer climate or annual climate we can understand in terms of how green the forest response is. And that's pretty neat. That's good, right? The fact that we can understand what's going on with the forest greenness index as a result of changing temperatures was a nice, is a nice result to have. It's really easy annually to model, you know, the cold time versus the warm time. But it was more interesting to try and figure out what was going on. This shows, in this case, each of these graphs here shows the relationship between what we observed and what we predicted when we tried to model summer photosynthesis. Resolution's not great on this guy. So this is the predicted photosynthesis scatter plot. This is the versus observed predicted photosynthesis scatter plot for, say, the tundra plants on the left and the conifer forest on the right. And we're able to do a pretty good job of modeling just summer photosynthesis as a function of climate, which is a neat result also. And we found even something cooler. We found that the tundra greenness index responded to what was going on in that summer. So if that summer was warm, that tundra was greener that year. Okay, so it was a simple positive relationship between maximum summer temperature and greenness. So more photosynthesis in warm summers. Makes sense. Cartoon idea holds true. We found out with the forests, something the opposite was happening. We found out that what was really happening there is that if you had warm spring temperatures, you could get higher forest greening. Okay, good spring, good forest growth that year. But maximum summer temperatures were negative. Hot summer, declining forest growth. Which led us to know something interesting about the physiology of these trees. What's also neat is that in the areas that were dominated by spruce trees, which hold their needles for up to a decade, so the spruce can remember the climate that happened up to a decade ago. Because they grow their needles 1 year, they hold on to the needles for 10 years. So that if they have a good year and they put out needles in that year, they're remembering that summer that happened 10 years ago. Okay, spruce and other long-lived conifers can have very long memories like that. So we model what's going on with temperature and with satellite greenness just using climate variables. So that let us know that at least this climate index, this greenness index really pays attention to what's going on with the climate, which helps us know that we're really seeing what's going on in the forests. But we want to do more than that. We wanted to actually go on the ground and see what was happening with the trees themselves. Okay, not just take the bird's eye view and measure from space, but actually go down there and measure the trees and see what they're saying about what's happening. And so here's a paper that we did a few years ago that looked at the response of boreal forests to warming over the 20th century. And I could read you from the abstract, it doesn't make any sense, but just like that. But this was also summarized in this Scientific American article. We're using dendrochronological records here, tree rim records. And the Stern article says, 2 other dendrochronologists, Andy Lloyd of Middlebury College and Andy Bunn of Western Washington University, used every boreal tree record they could find and confirmed that the browning of the boreal forest was a pan-Arctic phenomenon. And although it predominated in spruce trees, it occurred in all boreal tree species. The exact cause of declining tree growth are still being worked out. But drought and heat stress are 2 primary suspects, because browning is observed more commonly in dry continental areas than in the southern part and in the southern part of each species range. So again, this is work that was described in the Scientific American article that we did, showed that in fact, not only was the satellite record showing declining forest growth, but the tree rim records are also showing declining forest growth. And again, it's sort of flying in the face of our conventional wisdom. But so we could just basically wait. I could sit around for the next 10 years and eat bonbons and like figure out what's going on with the boreal forest. But that wouldn't be any fun. And so instead, we actually are going out. We're continuing this work, and we're developing all these new tree ring records of boreal forest growth. This is a very lush site in the Lena River in Siberia, near the city of Yakutsk. We're trying to figure out what's going on with individual trees. We found something very curious. We found that although large areas of this forest are showing declining photosynthesis, some areas are continuing to show increased photosynthesis. And in fact, we found that individual trees in one forest stand, some of those individual trees are able to track temperature, and as temperature increases, they're able to continue their growth and sock carbon away in the stem and in the roots and in the leaves, while other trees in the same sort of tennis court-sized area were declining in growth. We don't really know what causes this phenomenon. But we try to figure out what percentage of the trees for any one particular site, a couple of hectares in size, what trees were responding positively to climate, maybe here in the green, showing the percent of trees that were positively responding to climate, the ones that were negatively responding to climate, so showing declining growth, and how that changed over, this is just, a half dozen sites from the Lena River. We were able to tie that, we did that at dozens of sites across the Arctic with good new tree ring chronologies. And we found something neat. We found that as you increase in latitude, as you go from, say, 60 degrees latitude north up to, here's 67 degrees latitude north, the number of trees in a population that are positively tracking temperature continues to go up. This nice relationship. So that you have a majority of the trees in the south here being negative responders to temperature. As temperatures go up, they decline in their growth. As you move up into higher latitudes, we find that as latitude increases, the percentage of trees that are positively correlated to temperature are increasing, and implying some sort of interesting change in the population dynamics that's going on within these forests. So we don't know what's going on. Are these trees becoming drought stressed in the summer? Are they running out of water in the latter part of the summer? Are these trees being released from a cold limitation and are able to grow better? We need to continue to do this work. We need to understand what's happening with water uptake, and we're using stable isotopes and other techniques to measure that. We found what's neat about this work is, this is from a paper we just came out in Global Change Biology. This shows the relationship between these tree ring chronologies and the Lena River as you move from the south up to the north. The rivers flow north of the Arctic Ocean here. And then what's shown over here in these green and brown patches are the percentage of the satellite signals that show these changes in photosynthesis over the last few decades. So the places that show declining photosynthesis versus increasing photosynthesis. And the records between whether the trees are responding positively to temperature and whether the satellites are agreeing with those trees follows the same route. So here we show browning forests overall, percentage of significantly trending greenness versus brownness trends. And as we move further north, that trend increases, as does the change in the tree ring chronologies as we move up. So this is pretty cool. So what it means is we're showing these changes in photons that are hitting a satellite sensor in orbit around the Earth. That's related, we think, that's related to how green the canopy is below. And that canopy greenness we can measure with tree rings on the ground. So we can essentially see these tree rings from space. And we can tie that directly into forest productivity. And our results continue to sort of surprise us. We found declining photosynthesis in the southern part of the range, increasing photosynthesis in the northern part of the range. But the southern part of the range is where all the primary production areas of carbon is stored. These areas to the north are very sparse and show don't have the potential to sock away a lot of carbon. So that's we talked a little bit. Showed you what's going on with the land surface change. The land surface is predicted to have this big feedback to the climate system. Okay? As the land surface darkens and as it becomes rougher and as the snow changes, you're going to have an increase of the long-wave portion of the radiation budget in the Arctic. You know, more domination of long-wave radiation budget as things warm up. Forests, contrary to our cartoon idea of how boreal forests should grow, we actually don't find boreal forests growing more vigorously. And we're able to see that both with NDVI, this greenness index, and with the tree rings, and we're able to relate that directly to what's going on with the climate. And so this is early days in this research, but it's surprising. What's neat about it is that over the time I've been working on this, over roughly the last 6 or 7 years, we're able to make progress in this field. We're able to understand that what we've seen doesn't match up with our cartoon idea. We're able to collect data that demonstrates that using a variety of different scales and a variety of different techniques, which is good. You should be able to find things using the different methods. And we're able to relate that to actually what's going on in the biosphere. And so the work we're doing now is continuing. We're continuing to develop new tree ring chronologies, and the satellite data keeps getting better and better and better as it gets old, as it gets longer. And we've got better sensors that have records that are starting to become useful. They're old enough, they're starting to become useful. This is my grad student Logan Berner here, who has finished up. In case you're thinking about graduate school ever, this is Logan eating a peanut butter sandwich in the Northwest Territories. And moments after taking this, Logan was sufficiently tired that he popped that peanut butter sandwich in his mouth without removing his bug net first, and tried to jam it straight through. And I can tell you, there's nothing that the flies like better than peanut butter and jelly crammed into a mosquito head net, which turns out to be very difficult to get out. Logan suffered tremendously for science, but did very good work. Success in graduate school is largely understanding, it's like embracing your inner nerd and then understanding how much tedium you can withstand. That's basically what grad school is all about. It's actually more fun than that sounds. Logan's work, which was neat work, which was just published in the Journal of Geophysical Research. He looked at just the relationship between tree growth, the correlations between ring widths, and the NDVI signal from space. So how well can we actually see what's going on directly from space? This was a sort of simple result, but it was a really neat result. So it showed that these different species of trees were able to actually get significant correlations between NDVI and tree growth after adjusting the significant tests for autocorrelation. But the correlations are kind of weak. Like if you take a tree ring chronology and you take the last 20 years and you line it up against the satellite record, you get a correlation coefficient of something like 0.4. Explaining 20% of the variance, right? So it's like so what, right? It's sort of one response. That's actually not that great of a signal. But the stuff that Logan did was really neat because he was able to show that what we do is we go to these areas. We'd either go in by float plane in the summers or travel on big boats on rivers. And we get to an area, maybe set up a camp, that's really close to rivers. You can't walk that far from the river. It's really tussocky and hard to walk. We set up, say, a site right there, and then we core maybe every tree within we'd be there for a day, and core maybe every tree within a couple hectare area, and then get that record. And so here's showing a 250 square meter area. We would never even get close to that, right? We just get this tiny little area right in next to the river, and we're always going to be close to the river. We got those trees, and we measure what's going on in those tree rings. And we kind of think that should have something to do with what's going on in the canopy, right? But it turns out the satellite can't see this spot, right? The satellite can't even see this 250 meter circle. Nor can the satellite see this 750 meter circle. The long satellite records that we have, which go back to the early 80s, actually have an 8 meter footprint. Okay, so we're down here in this sort of a couple of tennis court sized area, coring trees, and we're able to show the response of those tree rings to this canopy, this incredibly heterogeneous, diverse landscape at sort of an 8-kilometer resolution, which I thought was pretty neat. But again, the correlation coefficients were weak, didn't give us a whole lot of confidence in what's going on. There's bugs, there's fire, there's clouds, there's water. But some other work that Logan did that was super cool was showing how this is called autocorrelation functions, and this shows how well the relationship you see in one year is related to what goes on in the next. It's essentially a measure of memory in an ecosystem. And when you see things like spruce, okay, up on top we have tree growth, how autocorrelated tree growth is. And we know that tree growth in spruce is really autocorrelated because they hold their needles for a long time. So that means that in the year T was really strongly correlated to what happened the year before, T-1. Okay, the tree T-1 had a good year, the tree the next year is going to have a good year, it has a lot of stored carbohydrates. And as you go back in time, that correlation sort of falls off. Okay, so in this case, these spruce trees are autocorrelated for about 5 years, which is impressive. What was neat about this work that Logan did is he showed that the satellite signal also had the same sort of shape of autocorrelation function. The satellite showed the same autocorrelation, meaning it was actually sort of seeing what was going on in the trees. Larch, which grow new needles every year on the left, don't have that same kind of memory. They don't have a lot of stored carbohydrates. They don't remember the past very well. And neither the trees do on the top nor the satellites on the bottom. And so this helps sort of us understand that what we were seeing in the satellites really was what was happening with the trees on the ground. So it's this ongoing sort of research work we have. And we've got a lot of work, sort of left to do. In this Stern article in Scientific American, really sums it up. It's not just the ice that's changing. It's not just polar bears that are changing in the northern high latitudes. There's these big changes going on the land surface. And there's these links between the satellite greenness indices, the climate, and the tree growth. They're all related, and we're just starting to get a good understanding of the relationships between those. But we're still a long way from actually knowing what's going on with the Arctic carbon system, with the terrestrial carbon budget. Like, we're a long way from figuring out if the carbon bomb is indeed poised to go off or not. We have a long way to go before we understand net ecosystem production. And I'll wrap up here. There's a couple things we're doing which are helping to get at this. I'm working with someone that studies soil restoration. When we're trying to model soil restoration across the Arctic. So soil restoration is how much carbon's coming back out of the ground through cellular respiration from bacteria and from the plants themselves, autotrophic respiration. And we're these really great models between different satellite indices and soil respiration. So we're actually maybe able to not only model photosynthesis from space, but maybe also soil respiration as well. That would be a huge advance if we're able to do that across the Arctic. This is a paper we have in review right now at Geophysical Research Letters. And we're able to try and actually estimate how much carbon there is on the landscape. This is work we did. We actually don't even know how much carbon there is in, say, tons of biomass per hectare. And we're trying to figure that out across Russia and across the US. So there's these basic accounting work that still has to be done to figure this kind of stuff out. And then if we can get that right, we'll be able to put this into models which will be able to tell us what the constraints are. So what's limiting this boreal forest growth? This weird thing happened where boreal forest didn't appear to be limited by temperature. So why not? Is it drought stress? Well, if it's drought stress, we should be able to show these. We can show them these physiological models that show what's going on here in the trend in boreal forests and how that relates to what's happening in the forest versus what's happening in the tundra, and whether this change in net primary productivity, which is actually what we want, how many grams of carbon are being stored per meter squared per year, whether we can understand those trends in relation to things like vapor pressure deficit of the atmosphere or low air temperatures. And so we're just starting to get this. It's a really exciting field to be working on. And the last thing is that we're trying to get a handle too now on what's going on in the correlation between what goes on in the primary productivity of forests and the mortality rates. Globally, we know that the more productive a forest is, the more net primary productivity there is, the faster the trees die, the higher the turnover is. We actually don't understand why. Amazingly enough, we don't understand the mechanisms between that. So this is a paper we have coming out in Ecological Monographs, which talks about the relationship between forest productivity and net primary productivity, which we're trying to improve. And then the work we're doing right now, the fieldwork I did this summer and the fieldwork we'll do next summer, actually has to do with taking tree growth measurements and relationships with these neat instrument towers called flux towers, which actually measure gas exchange from the soil, forest floor, all the way through the canopy, and measure photosynthesis and measure respiration directly with instruments. And right now we're measuring forest plots all around these instruments to try and figure out what's going on exactly with net ecosystem exchange. And it's been a neat journey for me as a young scientist to come up with this very unusual result and to start chipping away at what the answer might be and to start to make progress on it. And we're just starting to make good progress. And the coolest thing about it for me as a scientist is that Todd and I's academic grandfather, both our advisors, our advisor's advisor was a guy named Hank Schugert, who was a global change modeler. And Hank used to say that the best thing about studying the Earth, the most exciting about studying Earth system science was that there's only one Earth. So statistically, n equals 1, and the degrees of freedom equals 0, right? You can't do experiments. You got to get out there. You got to study and do the best you can. So I'll stop there, and I'll take any questions you might have.